Hi! In this lesson you will learn how to implement the greedy algorithm for the fractional knapsack, how to estimate its running time, and how to improve its asymptotics. Here is the description of the greedy algorithm from the previous lesson. While knapsack is still not full, we select the best item left, the one with the highest value per unit of weight, and either fit all of this item in the knapsack, or if there's only a few space left in the knapsack, cut this item and fit as much as you can in what's left in the knapsack. And then repeat this process until the knapsack is full. In the end, we return the total value of the items taken and the amounts taken. We've proven that the selection of best item is a safe move, and then after we've selected the best item, what we've got left is a knapsack with a capacity which is less, but the problem is the same. You have some items and you have a knapsack of some capacity, and you should fill it optimally so as to maximize the total value of the items that fit. So this greedy algorithm really works. Now let's implement it. Here we have a procedure called knapsack. It starts with filling the array A with amounts of items taken with zeros, and the total value we also initialize to 0. And then, as we said on the slide, we repeat for n times the following iterations. If the knapsack is already full, then in the variable w we will have 0, because in the start we have in the variable w the total capacity of the knapsack, but each time we will put something in the knapsack, we will update w, we will decrease it by the amount of weight that we put already in, and so in the end, when the knapsack is full, w will be 0. If w became 0, it means that we should just return the total value and the amounts of the items that we took. Otherwise, we should select the best item. The best item is the item which is still left, so wi is more than 0. And out of all such items, it's the item with the maximum value per weight. So the one which maximizes vi over wi. When we've selected the I, we determine the amount which will we take. It is either the whole wi, the whole of this item, if it fits in the knapsack. Otherwise, if the capacity of the knapsack is already less, then we just fill it up to the end. So A is minimum of wi and big W. After we've selected the amount, we just update all the variables. So we update wi by decreasing it by A, because we took already A of this item. We also increase the amount A of I corresponding to the item number I by the value A, and we also decrease the capacity left because we just decreased it by A by putting an A of item I. Also, we increase value V by this formula A multiplied by VI and divided by WI. Why is that? Because we took A of item number I, we took A units, and 1 unit brings us amount of value equal to VI over WI. So if you take A units, the total value by this item is A multiplied by VI and divided by WI. After we do n iterations, or maybe less if the knapsack is full before we do all n iterations, we return the total value and the amounts in the array. Now, the running time of this algorithm is big O of n squared. Why is that? Well, first we have the inner selection of best item, which works in linear time, because basically we have to go through all the items to select the best one. And we have the main loop, for loop, which is executed n times, at most, maybe less. So in each iteration we do some linear time computation, and we do this at most n times. That means that the total running time is big O of n squared. Now we can improve on that, because if we sort the items by decreasing value of Vi over Wi, then it will be easier to select the best item which is still left. Let's look at this pseudocode. Let's assume that we've already sorted the input items such that V1 over W1 is more than or equal to v2 over w2, and that is greater or equal to the fraction for the next item and up to vn over wn. Then we again start with the same array of amounts and the same total value filled with zeros, but then we make a for loop for I going from 1 to n, and on each iteration I will be the best unit which is still left. So in the start of the iteration we check whether we still have some capacity in the knapsack. If it is already filled, we just return the answer. Otherwise, we know that I is the best item because we didn't consider it previously, and it is the item with the maximum value per unit out of those which we didn't consider before. So we determine the amount of this item with the same formula, and we update the weights, the amounts, the capacity and the total value in the same way as we did in the previous pseudocode. The only change is that we change the order in which we consider the items, and this allows us to make each iteration in constant time instead of linear time. So this new algorithm now works in linear time because it has at most n iteration, and each iteration works at most in a constant time. So if we apply first some sorting algorithm to sort items by decreasing value of vi over wi, and then apply this new knapsack procedure, total running time will be n log n, because sorting will work in n log n, and the knapsack itself will work in linear time.